What happens when a statistician names a recently discovered dinosaur with one hump that's symmetric about the median? You get a normal curvosaurus. Get it? All right, so we're going to start working backwards from percentages. So I'm going to tell you we want a certain percent or in a percentile, and then we're going to figure out what values that corresponds to. In this example, adult male heights are on average 70 inches, 5'10", with a standard deviation of 4 inches. How tall must a man, adult male, be to be in the top 10% of the height? So what does the top 10% mean on the curve? Well, it's going to be this right area. But usually when we're getting z-scores for percentages, it's always going to be the left area. So there's 90% of the area is on the left, and the z-score that would correspond to the top 10%, we're actually going to look for 0.9 in the table. Not in the columns, so in the actual table. So where is that? 0.9, I'm looking around. Oh, that looks really close. There it is. That's very close to 0.9. It's even closer than that one. So to get the z-score, I go along this row, because remember our columns and our headers give us z-scores. It's 1.2, and the column has an 8 in the hundreds place. So it's this number plus that number is 1.28. That's your z-score. Now, it's way easier to get a z-score on your calculator. First of all, you're going to press second in distribution, just like you did when you did normal CDF, except now you're going to scroll down to inverse norm and press enter. Enter the area to the left in a parentheses and enter, and that will get you the z-score for that area. Let's go ahead and return to our example. How tall must an adult be to be in the top 10%? So we know this z-score is 1.28, so I can start with that. Let's get back to our formula. Z equals x minus mu over sigma. So your test statistic equals your value, your statistic minus your parameter all over your standard deviation. All right, substituting in, we know the z-score is 1.28. We know mu, the average, is 70, and the standard deviation is 4. We can go ahead and cross multiply that. 4 times 1.28 is 5.13. Add 70 to both sides, and you get 75.13 inches is how tall the person should be. Now we'll look at how tall an adult male must be to be in the top 5% of male heights. Top 5% means 95% are below or to the left of this z-score. So I'm going to do z equals inverse norm of 0.95, and I get 1.645. Let's bring up the formula. The 1.645 will go there. I know 70 is still the average and 4 is still the standard deviation. I can cross multiply and get 6.58 is x minus 70, adding 70 to both sides, 76.58 inches, and you're in the top 5% of male heights. Let's go ahead and look at another example. A tomato box filler is designed to get an average fill of 80 ounces or 5 pounds with a standard deviation of 4 ounces. Now, we want 95% of boxes will weigh at least how much? Well, that means that 95% weigh a certain amount or more. That's the top 95%. The top is the 95%. The bottom here is the 5%. So instead of doing inverse norm of 0.95, I'm going to say inverse norm of 0.05 because I'm on this side of the curve. And that's negative 1.645. We expected negative z-score when we're below the mean. And I know my formula is z equals x minus u, a mu over sigma. Go ahead and substitute. In this case, we have 80 ounces our mean, and apparently I did 4 for my standard deviation again. Cross multiply, and I can get negative 6.58 ounces equals x minus 80 ounces. Add 80 to both sides, and there's your answer. 95% of boxes will weigh at least 73.42 ounces. All right, suppose the company wants to have 95% of the boxes weigh at least 76 ounces, and they plan to adjust the average weight setting. What should the new setting be? So X is 73.42 ounces, And what I want is the difference between the target and the current is 2.58 ounces. So basically, what I'm going to do is increase weights by 2.58 ounces to 82.58 ounces. Pretty straightforward, really. Now, they can slow down the production line to minimize variability. If they want 95% of the boxes to weigh 76 ounces but still have a mean of 80, what should they set the standard deviation to be? So 95% weigh 76, and this is 80 here. So inverse norm is going to be 0.05 because I'm on the left side. That's negative 1.645. Go ahead and substitute that in. I'm solving for sigma here. So when I cross multiply, the sigma ends up over here. Divide both sides by negative 1.645, and I get 2.43 ounces. In this example, we're looking at an ice cream filler that puts an average of 32 ounces in a quart-sized container with a standard deviation of 1.5 ounces. The container has enough space to hold up to 34 ounces of ice cream. Now, they want less than 2% of their containers to be overfilled. How should they adjust the average to have less than 2% of the containers be overfilled? So their old average was 32 ounces. The new average we're trying to figure out, standard deviation is 1.5 ounces. We want the probability that the volume is greater than 34 ounces be only 0.02%. I mean 0.02 or 2%. This means that this Z-score is above 98% of the containers. 98% of the containers are going to have less than 34 ounces, which means that I want inverse norm of 0.98, which is 2.054. I'm going to go ahead and substitute back into the formula. 2.05, 34 is how much the x is. We're going to figure out what the mu is. 1.5 is sigma, cross multiply. And we get 34 minus mu, add 34 to both sides, and you get the new average should be 30.925 ounces. So now instead of trying to change the average, they're going to keep it at 32 ounces, but they want to change the standard deviation. In other words, they're going to slow down the line so it can be more precise, less variability. And so that means our mu is still 32 ounces, our new sigma is question mark. Probability is still x is greater than 34 ounces is 0.02. Same z-score, which is 2.054. Same formula. Let's go ahead and put that 2.05 over on the left, 24 minus 32 on the right. Cross multiply, divide both sides by 2.05, and you get your new standard deviation is 0.98.